Okay, thank you very much. I'm going to talk to you about the work that I've been involved with for the last 3 decades, and our sort of greatest strength is the fact that we're sort of a team of 3 musketeers with Dmitry and Alicia. We've been together now for almost 25 years, and that really has been the key strength of our group. So atomic and molecular collisions, well, firstly the statement is that they go on all around us. In this room right now we have collisions between nitrogen molecules, oxygen molecules, and this is a good thing. It gives us the temperature we have here right now. If those collisions were to stop, we'd have absolute zero and we would not be very comfortable. But those sort of kind of collisions, they're not particularly interesting in terms of applications, but you can include electron scattering on atoms, molecules, positron scattering photons. And I'm going to give you, just through animation, some of the things that we do. We begin on the left-hand side with the Positron Gun. It will set you back a couple of $1 million if you want to make one. We did so in our Centre of Excellence for Antimatter studies at the ANU. And you can scatter it on various atoms and ions. And these are the kind of potential processes that go on. Our job is to calculate the probability of any excitation to any of these excited levels, probability. So this one here is, for example, lighting industry for electron scattering would be interested. In fact, these fluorescent lamps here is just electron scattering on mercury, so they're particularly keen on the transitions that generate as much light as possible, as efficiently as possible. That last one there is called Positronium Formation. Positronium is an exotic atom. It lives for as long as 10 to the minus 9 seconds before they annihilate. But it's a critically important applications in positron emission tomography, so in detecting cancer. And also it sort of counts as a charge exchange process, a prototype of a charge. So we had an electron here, we had a charged particle come in, and then we have a charge exchange from here to here. So we can readily replace positrons with protons, and these are all the sort of things we do. And we have to predict where everything will go after collision, just in terms of probabilities. So we have to calculate everything. So this is what it is that we do. And such collisions are very difficult to calculate. Hard is good. Hard means that others will walk away and leave the problem to us. So what are the issues? Governed by laws of quantum mechanics. So this is not classical physics. We have to calculate probabilities. If you want to calculate probabilities, you need to work with what are called unitary theories. You have to ensure that all of the possible reaction channels are taken into account. And this is awkward because it's countably infinite discrete states for atoms and molecules. There's an uncountably infinite target continuum. That means when you eject the particles, it can take any energy it likes, as long as there's energy conservation between the particles. And then to make things more interesting, charged particles interact out to infinite distances. And of course, computers don't really like infinities very much. So all of these things need to be put in a computationally tractable way, have fundamental mathematics underpinning all this to ensure that when you do your calculations will convert to the right answers. And lastly, that example of positronium formation is an example of multi-centered collisions. So proton or positron collisions with atoms, they can grab the electron, and that makes it at least a 2-center problem, which means you have to use different coordinate systems perhaps, and we're working on new ways of doing that in a more general way as well. So this method, converging close coupling, is something that we developed in the early 1990s, and its great and still unique strength is it is valid at all energies and for all of the collision processes. Prior to us starting, there were separate fields for low energies, high energies, intermediate, electron scattering versus positron scattering, photon scattering. All these were different fields, all in the one hit managed. We've made a career out of it now, almost 460 publications with a lot of co-authors, a lot of citations, and we've been very fortunate with ARC funding over the years. So what are they good for? So primary motivation is to provide accurate collision data for science and industry. So we are working in the field of atomic and molecular physics. We know all the particles, what they are. We have nuclei, we don't break them up, we don't have enough energy to break up the nuclei. And then you have the electrons, right? So there's energy through, say, photons. We know what all the particles are, we know what all of their interactions are. There is no excuse not to get things right. So if you want to be useful and engage with industry and provide useful data to other science, of course you want to avoid the garbage in, garbage out situation. So the niche that we have is we provide highly accurate data. So the applications include fusion energy. So this is the largest scientific project on the planet. It's called ITER. ITER stands for International Thermonuclear Experimental Reactor. People often joke that fusion energy is always 30 years away. That still is the case. But this is about this way up being built in Cadarache, France. If you can see the scale, this is a person up here. This is a big thing. I've been to that site. One of my colleagues is there now. The first plasma is scheduled for mid-2020s. What's the goal? The goal is to basically replicate the core of the sun deep inside here through very, very highly energetic collisions that will get fusion burning. Of course, all the particles will interact. You've got that are made of beryllium. There'll be some lithium in there as well, and these are light elements that we have very accurate calculations for. And the key thing with these things is that you'll have a lot of energy losses. So one of the very large big expenses is they have to build a huge power plant to try to ignite this, to get the temperature going up. So you have to know all of your energy losses before you know how big the initial energy submission has to be to the system. And the goal of ITER is to generate 10 times more energy than what is put in. So at JET, in Culham Laboratories, they've already broken even, I think, in the 80s. So we know that the ideas will work. Hopefully this is of sufficient scale to generate 10 times more energy than what is put in. And if that's the case, the next reactor is going to be called DEMO, and its job will be to generate electricity. Another group that we work with is Cern. Most people would have heard of the Large Hadron Collider at Cern, and they're famous for discovering the Higgs boson. But what they also have is a beam of antiprotons, which is a fantastic, it's the only place in the world where you can get that, and that has the capacity to address two fundamental problems in physics, both of which, if solved, will lead to a Nobel Prize. One is matter-antimatter asymmetry in the universe. Nobody understands why there is that asymmetry. And another one is that because there is no unification between quantum mechanics and gravity, nobody knows how antimatter will behave under gravity. It's that simple. So if you make some antimatter, how will it behave under gravity? There are, let's call them exotic theories that suggest you'll have anti-gravity, but not too many people really believe it, but you have to do the experiment. However, if you want to do a gravity experiment, you must work with neutral matter, because electrostatic forces are way overwhelm anything gravitational. So you have to work out how to make neutral antimatter. And of course, if you start with antiprotons, well, it's a charge of -1. So you have to combine with a positron and create anti-hydrogen. So that example that I showed you of forming positronium, if you run it backwards, it's in fact positronium could come in on a proton to form hydrogen, or could come in on an antiproton and form antihydrogen. So we provided calculations that follow this particular mechanism. It looks a bit on the complicated side, but so you have positrons come in. What's the Positronium converter creates positronium, laser excite positronium, have highly excited states of positronium. That's a good thing. You're moving them further apart. It means they live longer, larger object, bigger interaction cross-section, greater probability of forming antiproton when you bring them from an antiproton trap, bring them together, and out comes the hydrogen beam. So anti-hydrogen beam. Once you have an anti-hydrogen beam, you can just say, watch. Does it fall? No. Does it go up? Does it go down? Nobody knows. But you have to make that, because this is a physics, you have to make anti-hydrogen in sufficient quantity to do this. And this one here, I'll play this, this is a charge exchange process. Okay, here's the sun, bit of solar wind coming across, an interstellar helium atom minding its own business, a solar wind oxygen ion comes across. Here's a charge exchange process, grabs that electron, because this is 6+, it's really highly charged ion, and by probable level to go to in that transition from the helium, ground state of helium, to oxygen 6+ is by velocity matching. So it will go to a state of a similar velocity to helium, and that happens to be an excited state of the oxygen 6+. Once it's bound there, it's unstable, so it drops down to the ground state and emits X-rays. And the population of all the kind of X-rays that can be emitted through this process can, if you detect them all, you can work out what was the projectile and what was the target. So a field that we have a lot of application in is medical areas. So medical imaging, this is an example of a PET scan. All of our hospitals have got that. That uses positron collisions. So what happens there, if you suspect a patient has a tumour in some inoperable area, you would get the patient to drink a liquid that has had a glucose added that are positron emitters. And because cancerous cells grow very rapidly, they need a lot of energy, they love sugars. So they preferentially absorb those sugars, and so they preferentially emit positrons from those particular tumours. Positrons then leave at very high energy through lots of collisions, they slow down. We need to know the stopping power. Right? And then they slow down, they form positronium. Positronium lives, as I said, 10 to the minus 9 seconds or so, annihilates, 2 gamma rays go out in the opposite direction, go straight out of the body, get detected in a coincidence, and this way we can know all the hotspots where the tumour is. And the key issue, if you know all of the stopping power and all of the collision processes, this is not so easy, because the brain is, reasonably well modelled by, say, water molecules, but this is a work in progress to improve the accuracy, because you really want to know the boundaries of tumours. Because there's another fantastic new treatment involving collisions, this time with protons. It's typically called targeted proton therapy, that when you bombard materials with heavy projectiles, those projectiles lose their energy right towards the end of their travel. In other words, with this particular system, now, conventional radiation therapy has a huge entrance dose, has a huge exit dose, a lot of side effects, particularly in the brain. With this targeted proton therapy, if you get all your calculations right, you can provide the destructive energy of the protons just to the tumour, as long as you know exactly where it is. And the last part is going to say a little bit about the computational implementation of the converging close coupling method. So it's developed in the early 1990s, and what we have to do is we have to find this quantity here. It's called a probability transition amplitude. So here's what the meaning here is: you have incident projectile momentum Ki on an incident target in initial state phi I. This is a transition operator for a particular total spin in the system. So electron hydrogen will be 0, 1. Then here's your final state of the target, final projectile. And to calculate all this is why this is called coupled close coupling equations. You can't get just the transition that you're after. It all couples back to itself. These are known as Lipman-Schwinger equations. A Nobel Prize was awarded for this particular kind of formalism, and to try and simplify what it really means in terms of large operators or matrices. So we have T equals to V plus V, there's the V, G is the Green's function, the division here, and T again here. And we convert that to a set of linear equations. So we simply take VGT out to the left-hand side, and I minus VG is our matrix A, T is our known, it's our X, and V is known. So our big job is to calculate all of this. Once we have all of this, then we can construct a large matrix equation and call LAPACK or ScalarPACK and get our answer. So this is what we do, and this formulation is done in such a way that it has a dependence on the size of the bases that we use inside. So I've written here an n dependence over here, because as n is increased, in principle everything changes. The equations get bigger and bigger and bigger, but of course you want your final answer to converge to something. You don't want your final answers to be dependent on your basis. So fundamentally this is a kind of problem that can get larger and larger and larger depending on the level of precision. So once you set it up, you keep on increasing your basis sizes until you have convergence, and you check that your convergence is to the right answer, either by comparing with experiment, but typically what's more fun for us is when we disagree with the experiment and then we say, nope, the experiment must be wrong. This has now for the first time been shown where the target is a molecule. People have had molecular targets thought to be so complicated, no theorist had ever had the courage to say, if they disagreed with the experiment, that the experiment might be wrong. Well, we're there now, and that's only possible through the calculations done here. Okay, so just a little bit of a history of evolution. So we started with a single CPU. At one point in my career, I paid $60,000 for 512 meg of RAM, and money well spent. I'm here in front of you because I did. Mid-1990s, implemented OpenMP, symmetric multiprocessing architecture. Now, for quite a while, there was quite a tension in the in the evolution of the hardware. Will we go towards highly distributed processing? So it's a machine called thinking machines, I think it was called. And I was terrified, because to go to that kind of architecture would require complete rewrite of the code. But then OpenMP, the symmetric multiprocessing machine, seemed to win out, and that was fantastic for us because there's no rewrite of the code, because it came with more RAM, and if you have suddenly 20 cores, that's an order of magnitude increase, because we always had written our code in such a way where very few lines of code would take up all the time. It was a deliberate strategy, so that as the architecture improves, you was ready to take advantage of it and just work on those small areas and get massive speed up. So that was fantastic, and took us up to about 100,000 by 100,000 matrices. And the next generation of parallelization, just before I became head of department, my last bit of useful contribution to the group is implemented MPI to split the matrix across this new architecture of loosely connected fat nodes. Maybe I should call it MPI connected fat nodes. I can't emphasize enough how much we appreciate that partnership of us as scientists with yourselves as experts in the technology that is evolving. When we work together, fantastic things happen. And last fortnight, we're now hitting the third generation of major speed up. It's fantastic. On the very first day, I quickly realized we're there again. It's time to do things differently. In this last fortnight, I began to rewriting the OpenMP parallelization, redoing all of the looping, and already had a go to dump a whole lot of things in one hit, do a lot of for us it's basically dot products, and we've got a factor of 10 improvement. which is phenomenal. And yet he has not yet been able to implement parallelization across the 4 GPUs over there. Well, we're on our way. So we have done the proof of principle, and I had a lot of fun doing this. So we couldn't have done it without Ivek and Pawsey. Our careers critically depend on the architecture here and the fact that it's up to date, it is at the world-class level. That means we can be competitive with people because they'll have access to the latest and greatest machines, and it matters. Thank you very much.